So before we get into the details, so let's quickly recall some notations and definitions. Okay, so recall derivatives, and rate of changes, rate of change. Derivatives and, well, I should say rates of change, but yeah, rate of change. So when you talk about f prime of x and you evaluate at some input level x equals a. So here, this is one way to write down the evaluation of the derivative at a point. Right, of course, you can write it as what? F prime of a. So basically, this is just saying, okay, for function, I'm writing out a vertical bar indicating that, okay, for that subscript, that's gonna be the point at which I'm evaluating the function f prime. So that's the same as saying I'm just plugging f prime, the input to be right? And by definition, this equals to the limit when here I'm using h to indicate the change in the input. Okay? So you know that the derivative is going to be the limit of the average rate of change when you change the input by h units, right? So this is f of a plus h minus f of a, and the change in the output if you just increase the input by h units from the input value a, right? So here, if you're looking at this fraction, this is the average rate of change on the interval from a to a plus h, right? Average rate of change. But then when you take the limit, this thing becomes the instantaneous rate of change. So, or you can think about the circled part as what? The slope of the secant line, right? Where your input just changes from a to a plus h, right? And then now you make the length of the interval h smaller and smaller, approaching to zero. Then you are essentially using the secant slope to approximate the tangent. Right? All right. Now let's talk about the partial derivative. So the partial derivative is actually highly related to a univariate derivative. So basically, the partial derivative is an instantaneous rate of change. Instantaneous rate of change when all the other variables, are treated as constants, okay, are fixed. Example. So basically now, this sentence right above is the idea of the partial derivative. So let's say you have two variables, then the partial derivative with respect to one of the variable is that you just fix the other variable as a constant, right? And in that situation, only the variable that you're looking at is changing. So now you are restricting yourself to a univariate case. Okay, so that's exactly the idea. Now when you're at the univariate case, you can just take the derivative. But now this is only looking at one of the variables, so that's why it's called partial. Okay. Example. Let's look at f of xy, which equals to x squared plus y squared. We want to find the instantaneous rate of change with respect to x at the point 2, 4. Okay. So here we only look at the instantaneous rate of change with respect to x, right? But we want to look at the location 2, 4 for this function. So this tells you what? This tells you we are only changing x, but we are fixing y, right? And we're fixing y to be 4. So fix y to be 4. Then this tells you what? This tells you, okay, we don't really have a binomial function anymore. So if you fix y to be 4, then you get to a univariate function. So f of x now. So instead of y, we have the evaluation of 4, right? So that tells you I'm looking at x squared plus 4 squared, which is 16. So this is the restricted function, only in terms of x that we have. Right? So now, indeed, we can take the derivative with respect to x. Okay? But now here, let's call this function g of x. So let's call this function g of x as the restricted function where our y value is 4. So now, if we do this do this notation, then g of x is a solely univariate function, right? So in this situation, we can write down the derivative as g prime. So g prime of x, now we can just differentiate. So this is nothing new. Okay? So this is really old. So x squared gives you a 2x for the derivative. 16 is a constant, so it gives you a 0. So that's easy. And then, okay, so now we specified 4 for y value, and then we have the instantaneous rate of change for whatever x value, but here we want to know the behavior at x equal to 2, right? So we just get the x value and plug in. So g prime at 2 is 4. So we just plug in x equal to 2. Hence, we can conclude that, okay, the instantaneous rate of change is actually 4, right? So hence the instantaneous rate of change with respect to x is 4 at the point 2. Okay. Any questions so far? So really clear, right? So here, when you talk about the partial derivative with respect to x, then you're just fixing y as a constant, okay? But here we even specify the location, so it tells you, okay, my y value has to be fixed to be 4. And then now, once we take the derivative, then we plug in x equal to 2. Okay, so that's the process. So in general, it's the same idea. Definition. So the partial derivative underline. So f of xy. So there are 2 of them. Okay, so one of them is about well, one of them is with respect to x, the other one is with respect to y. Right? So when we do the notation, it's going to be f sub x of xy. So the subscript x is just telling you, okay, this is a partial derivative with respect to x. Okay? And when you define this partial derivative you just think about fixing x, fixing y, and only changing x. Okay, so when you do that, so when you change x, what do? Is you have the prior input x and then later input x plus h. Okay, so the change in input is exactly h units. And here you only change x, but fixing y, you just don't touch y at all. Okay, minus. So you still have this kind of average rate of change for fraction. The only difference here is that okay, I'm playing with the input x. It's x plus h, the latter input minus the prior input where the x value is just x. Okay. But you see the typo here. So when I'm talking, I may mess up with this. But the y is not changed at all. Okay, so we don't touch y. You see, fixing y first and then taking the partial with x. Okay, was it good? And now, of course, you can think about the definition of the other partial, right? So now, if you do the partial with certain y, let's just say what? Let's just say I'm not touching x at all. I'm only doing a slight increment on the y value, and then I want to do the rate of change. Okay, so now it's f sub y of xy. It's going to be the limit when the increment of the input is now h again. So the change in input is h. Change of output is going to be y plus h minus. Okay, so the latter output is with respect to y plus h as the input, and then the prior is still the original output. So in this situation, x is not changed at all, and we only do the instantaneous rate of change with respect to y. Right? Remark. If we fix, let's say y equal to a constant a. So when we fix y to be a constant, then this is again reducing the function to be a univariate. Okay? So if you fix y to be a, then you have f of xa, and we just denote it as g. Then now g is a univariate function, so this is exactly the process we have done just right above the definition, right? So we fix the y value, and then we have the g, and then we can take the derivative. So g prime of x is exactly, so think about g prime. G is a univariate function, so g prime is exactly the limit when the input h is well, the input is changed by h units, and then I'm gonna do the change in output over the change in input. Right? So the limits of this fraction. So this is definition of the univariate derivative. Right? But now we realize that g is exactly f of x a. Right? So you can write down the definition of g. So this is, so you see here we plug in x plus h. This is exactly as just plugging in the input x plus h in the first component of the f function, right? But the y value is just a. That's not changed. Okay? And now for g of h, that's just f of. So you see. Okay, so typo. So indeed, I'm getting old. So here, you somehow have to concentrate a lot when you're writing the command. So g of x, that's 7 g of x. So basically, okay, so this f of xa, where my y value is still fixed. Okay? That's it. And now you see, this is directly related to the definition that we have right above, right? So the only difference is that the circled y part is now just a constant a that we have done the evaluation. So, and you see, the value of y does not really affect this limit at all, because here what the change is only in the input at the first component, right? So by the definition that we just introduced, this most right-hand side is exactly the partial derivative with respect to x. And now here, only the difference is that y is now a constant. Right? So you can see when we do the partial derivative, when we are doing the partial with respect to x, then the y value doesn't matter really. Okay? So you can plug in the value of a first, and then do the limits when you take the derivative, or you can just do the partial right here, and then you plug in y equal to it. Okay? So the order doesn't matter at all. That's the point. Indeed. To find partial derivative with respect to x, regard y as a constant and differentiate the binary function with respect to x. So basically, when we do the partial with respect to x, we just treat y as a constant. So that's the only thing that we need to keep in mind. But that's very important. And similarly, if you're doing the partial with respect to y, then you just treat x as constant. Okay, so before we look at some examples, let me quickly also mention another remark about the notations. Remark. So here we see that we have two partial derivatives. We have f sub x, we have f sub y. So the original prime notation for the univariate functions, which will not be a reasonable notation anymore. Okay. So when you talk about f prime of xy, this is not a valid notation due to confusion of variables. So basically, when you have, if you only have a univariate function f of x, right, and you do the prime for that, then it's clear. Okay, we have only one variable. But now f of xy, we have two variables. So when you do the f prime, this notation, it's not really clear which variable you are differentiating. So that's why we have f sub x and f sub y here. And now, if we also denote the output of the function as z. So if z equals to f of xy, where z now represents the output variable, we have the following. Are acceptable notations of partial derivatives. So of course, we started with f sub x, right? F sub x of xy, this is the partial derivative with respect to x, where we treat y as a constant, right? But then we also realize that when you talk about f prime of x, and we can abbreviate x to just denote f prime, right? So here it's the same idea. So the input pair is not really that critical. So we just denote as f sub x. That's indicating that okay, I'm doing the partial observance. Okay, so here x, this partial is just denoted by the subscript. And also there's another way. So we can write what's called del f del x to represent the partial here also. So this is in contrast to df dx. Okay. So when we were talking about the univariate function derivative, this is what? This is the Leibniz notation for derivative, right? So we have df dx as the notation for the differential to be d. But here we are using a different symbol. Okay, so this is the del symbol, which is used for partials. So you can also write it as del x of f of xy if you want to include the arguments xy. And you can even write del z del x. Okay, so just indicating that this is the partial derivative of the final output with respect to x. And here we read this notation as del or partial. So it's really common that you read it as partial z partial x. And the notation, let me write it larger, just something like this. So it's like a different way of writing d, but it's just like this. So there's a few of these notations, right? And there are more. So here, if you write f sub x, so this is a situation where you have x and y as the inputs, right? If you have more input variables, let's say like n of them, where n is large, right? So then using 26 the English letters is not even enough, right? So then we can think about saying, okay, x is the first variable, x is the first input argument. So we just put f sub 1. You are doing the partial with respect to the first variable. And that's also acceptable. And then you can also write a cap d sub 1, just to indicate that this is doing the derivative when we are looking at the first variable. And also it's acceptable to put cap d sub x. So this cap d sub 1, cap d sub x, these are the operations of doing the derivatives and doing the partial derivatives. And then, okay, this is a really long list, right? And then for with respect to y, we have the parallel list. So it's going to be f sub y of xy, and you can abbreviate the arguments to be just f sub y, and you can do del f del y to indicate the function taking the partial derivative with respect to y, and you can also include the arguments by doing del y of f of xy, right? And now if you say, okay, I want to omit the function f of xy, but only represent the output argument, that's going to be z, right? So it's going to be del z del y. So this is very common in our course. And then, of course, if you have more variables, say you can just y is the second variable, right? So this is f sub 2. Or you can say the derivative with respect to the second variable function, or derivative of, excuse me, derivative of the y variable. So basically, in this course, multivariable calculus, then we don't really write the prime notation anymore for multivariable functions. It's still fine for a univariate function, but you need to be very careful. Any questions about the notation? So for these partial for this del notation, that's very important. That's going to be heavily utilized within our course. Example. Let's look at f of x, y. So let's look at some fundamental functions. Let's say f of x, y is x times y. So let's talk about the partial derivative with respect to x. Okay. So when you talk about partial derivative with respect to x, you're treating y as a constant. Right? So x times y. Now, treating y as a constant. This is actually a linear function in terms of x, right? This is just a constant number y in front of x, right? So if you do the derivative, what do you get? So for you just write down y as a constant, and then the derivative of x is 1, so it's just 1 times y. Right? So that's exactly y. Right? And now if you think about the partial with respect to y, it's the same idea. So f sub y of x y. And here, so I'm doing the partial with respect to y. I'm treating x as constant, right? So now we in front of y we have a constant which is like the slope of like a line, right? Linear function. And then it's the same thing. So keep that constant in the front, and then you do the partial. You do the derivative with respect to y. That's giving you a 1. So x times 1. So that's good. Okay, so let's look at more. Let's say we have f of x y equals now x to the 3 plus x squared y to the 3 minus 2y squared. We want to find f sub x of x y, f sub x of 2 1, and f sub y of 2 1. So we're looking for the partial derivative with respect to x for the function. We also want to evaluate this partial derivative at the point 2 1. And we also want to look for the partial derivative with respect to y at the point 2 1. Okay. So it's clear that we have to do the partial with respect to x and with respect to y separately. So let's do that. So f sub x. So basically, we are treating y as a constant, okay? So if you're thinking about treating y as a constant, then this is a constant that's multiplied by x squared, right? And this thing, negative 2y squared is an absolute constant. It doesn't change at all when your x value changes, right? So treating those as constants, and then we just do the derivative with respect to x. So the first term, x to the 3, you do the derivative, it's going to be 3x squared, so it doesn't give you anything new. Now plus, okay, so we know y to the 3 is a constant, so we just keep it there. It's constant multiplied in front of x squared, right? And now you do the partial with respect to x, so x squared gives you 2x. And we just multiply with that y to the 3 as constant as well. So that's good. And finally, what about the negative 2y squared? What's the derivative for that?
0.
It's a 0, right? It doesn't change, so it's a 0. So that's good. And now, well, there isn't really anything to simplify other than omitting that 0 here. So let's also quickly view the partial derivative with respect to y. So if we do, so basically, now x is a constant, so x is fixed when we do the partial derivative of 31, and this is also a constant. So x to the 3 gives you a 0 because it doesn't change when y changes. Plus x squared is a constant in the front. Y to the 3 gives you a derivative of 3y squared, so 3y squared. And minus, okay, the derivative of y is y squared is 2y, so it's 2y. So simplified input is 3x squared y squared minus 4y. Right? Basically, when we do the partial with respect to x, we're just fixing y as constants, and we just differentiate the x, right? And if there's any expression about y in front of the x expression, say it's just gonna be a constant multiplier in the front, right? When there's no x at all in that expression, that tells you okay, that y part is just a constant, doesn't change, and the derivative is gonna be 0. Okay? And the same thing happens for the partial derivative with respect to y. And finally, last time. I just added the evaluation part, right? So now you plug in the input pair 2, 1, it just says x equal to 2 and y equal to 1. So we can easily calculate the these are instantaneous rate of changes at the particular input pair. Okay, 2, 1. Remark. So the partial with respect to x and the partial with respect to y. You can see from our calculations that these are actually bivariate functions, right? These are functions of two variables. And the partial at the point 2, 1 with respect to x, and the partial at 2, 1 with respect to y, they are values of functions f of x and f of y at the input point 2, 1 respectively. So basically, for when you do a partial, it's gonna give you essentially a bivariate function. But then when you talk about the instantaneous rate of change, that has to be this bivariate function evaluated at the input point. More examples. So if everything is polynomial, that's definitely nice, right? But of course, we have something more complicated. We have seen something just now about trig functions, right? So let's say we have f of xy, it's gonna be sine of a fraction, x over 1 plus y. Okay, so now this is the composition. We can also calculate the partial for this kind of function because of what? So when you think about it, when you try to do the partial with respect to x, let's just say, okay, I'm fixing y as a constant. So if I fix y here as a constant, then this is just x over a constant inside the sine function, right? So this is actually, again, a univariate function with respect to x. So this, it's a compositional function, so we have to use a chain rule, but that's still Calc 1 material. Okay, so when you do the partial, now let's look at the Leibniz notation where we just use del or partial. So you can read this partial f, partial x, or you can read this del f, del x from before. So we should y as a constant. This is only argument x, right? So we have outer level sine function, we have an inner function, which is a fraction. So the chain rule here, yeah, let me write that the chain rule. So if you have the, let's say if you have f of g of x. Okay, so if you have this kind of a chain of functions, f composed with g of x, right? So this is gonna be f prime evaluated as the inner function, then multiplied by the derivative of the inner. Okay, so that's from Calc 1. Just keep that in mind. So here our outer function is sine, right? So we need to do the derivative of that, which is cosine. okay? And here we want to plug in that inner function, not changing anything. And then we multiply by the derivative of the inner, and here we're doing the derivative with respect to x, right? So the denominator is a constant, doesn't change. Only the x part is differentiated, and x gives you a derivative of 1, right? So yeah, let me write in two steps. So I'm gonna do the partial, so it's a chain rule. So derivative of the outer, evaluate the inner times the derivative of the inner. And then I write explicitly what the derivative is, what the partial derivative is. So here, once again, when I'm doing the partial derivative of x, y is not changing at all. Okay, so x part it gives you 1 over that constant, and I'm multiplying. That's good. So now you see the things gets a little bit more involved, right? You have composition, and of course you can write 100%. Okay. Of course, you can see that this fraction 1 over 1 plus y can be moved to the front of cosine. So it's just that's the same thing. So it's good. Okay, so now let's look at the partial derivative with respect to y. It's a similar idea. And the only thing different here is that now y is in the denominator, so it's a little bit more complicated. So del f del y. Okay, so it's still the same idea. So we have a composition, the outer is sine, so we do the derivative of the outer, which is cosine. We evaluate the inner function. Now let's write it again. So it's del y, and here we want to rewrite the inner function a little bit because it's a fractional function. It's kind of ugly. So we want to write it as a power function, right? So this is x over 1 plus y. So that's the same as saying, yeah, let me just write that. So x over 1 plus y. So in another way, I can write it as x as a constant, right? X is not changing here, times 1 plus y whole thing to -1. Okay. And now this part, we're gonna do the chain rule again, because here we have the inner as 1 plus y. The outer is something raised to -1. Okay, so the input raised to -1, that's the outer function. And then we just continue copying, so cosine in the front, it's gonna be copied, multiplying. So here, we're gonna do the, we rewrote the thing in red, and then we're just gonna do the chain rule again. And so x is in the constant in the front, multiplying, okay, I have something to -1, it's power function, right? So the derivative of the outer is gonna be -1 times something to -2. Derivative of the outer, I plug in the inner. And then for the derivative of the inner, it's just 1, right? So 1 plus y, the derivative with respect to y is 1. So basically, I would say in the exam, as long as you write it in this way, it's gonna be fine. You don't really have to simplify. So here I just want to rewrite it in the way that it's the products are clear. Okay, so you're actually multiplying by negative x 1 plus y holding to -2. Okay, if you want to write this as a fraction, it's gonna be okay, but here you don't have to do it. So it's good. So looks like it's still applying Calc 1 material, but now it's getting more involved. Because here we see, okay, the variable that you're doing is in the denominator, so you have to rewrite it a little bit. Right, example. So now we're gonna look at something more involved. We want to find the partial derivative of find the output z with respect to y. If z is a function that is implicitly defined by the following equation. So it's going to be x to the 3 plus y to the 3 plus z to the 3 plus 6xyz equals 1. So this is a very important kind of question that's called implicit differentiation. Implicit differentiation. Okay. So basically, if you recall, in Calc 1, we wait, let me think. Yeah, in Calc 1, you may have an equation that's just describing you the relationship between the xy variables. But the equation is so complicated that it's difficult to explicitly write down the function, well, the output y in terms of the input x. Okay, so in that situation, we're doing the implicit differentiation, and here it's the same kind of situation. We have here we have a degree 3 polynomial equation, and then if you fix x and y, you are able to determine the z value. Okay? But the equation is just too complicated. Okay, so in this situation, we know that z is implicitly defined in terms of x and y. We know it's a function, okay, but we just don't know the explicit expression of it, right? And here we are still able to do this kind of implicit differentiation. It's the same kind of idea, but you need to just adapt to the mind setting. Okay. Note that z is a function of x and y. Okay. So here, the only thing different is that, okay, z is treated as a function. It has two variables. Okay, so basically when x changes y, when x changes, z will change. When y changes, z will change. So that's the situation here. Now let's do the implicit differentiation. So what do we need to keep in mind? So when we are doing the partial with respect to y, that's saying what? That's saying, okay, I have two arguments. I have x and y. My y is changing, but my x is fixed as a constant. Okay, so that's the only thing that's different here. But then z, of course, z will be relying on y. Okay, so that's the rate of change we're looking at. Okay, so once again, x, y, z. Y is changing, z relies on y, x does not change. So that's the thing you need to keep in mind when you're doing this implicit differentiation. So let's do it. We have an equation, right? So we just do the partial derivative with respect to y on both sides. The partial derivative with respect to y on both sides. So let's write that down first. And we know this partial derivative will equal to the partial derivative of the right-hand side, right? So that's the left-hand side looks complicated, but the right-hand side is easy. So 1 is not changing, so that's a 0. So essentially, we will get an equation again. Okay. So that's good. And then we just need to just play with the left-hand side. Okay. So here, let me put it in red. So here, so we're doing the partial derivative of y, right? X is fixed. X fixed. Y is changing. Z relies on y. Okay. So z is a function. Okay. So now let's do this. So here we have x to the 3. That's giving you what value as the partial derivative? X, you said x squared dy of x. So well, if you're applying the chain rule, right? So x to the 3, so it's 3x squared if you do the derivative. But then you need to do the derivative of the inner, right? And this thing, so so here it's the thought process is very good. The only thing problematic is that okay, we're doing the partials, and that's one comment. And the second comment here is that the partial derivative of with respect to y of x is actually a 0, because here, like I mentioned, this x is actually fixed, right? So in this part is actually a 0. So the first term is eventually a 0. Yeah, I'm gonna put it here. It's a 0. Okay. So it's a very good thought process, but and draw the bracket a little bit. Okay, this looks nice now. All right. And now let's think about the second term. It's y cubed, right? So y cubed is now straightforward because we are doing the partial with respect to y. So we just do that. This is a power function. Okay, so power rule. So 3y squared. Okay, so we don't really have to do anything further. And now for z to the 3, it's going to be a similar process as this. The only thing different here is that z now is a function. Okay, z relies on y. Okay, so z to the 3, we still have to do that chain rule. So plus. So z to the 3. Okay, so it's a composition. It's a power function on the outside. Something to the 3. Okay, so when you do it, it's going to be something 3 times something squared. So this is the derivative of the outer. Evaluate the inner, and then we do the derivative of the inner. Okay, so del z delta y of z. And yeah, I want to move the things a little bit to the left because I do need a little bit more space for this line. So that's good. And you can see if everything is good up to now, we handled three terms, right? We have the x cubed, y cubed, z cubed. X cubed is fixed as constant. Y is just purely above y, so that's good. Z cubed is a composition, so we need to play with that. And finally, we have what? We have 6 times x y times z. So this is a product because 6x is fixed as constant, so it's constant multiplied in the front, doesn't affect anything. Y is changing, z is relying on y, so z is also changing. So we have a product of 2 functions. Okay. So plus. So yeah, it's not that straightforward. So let's just write another step. So we have an intermediate step. So we are doing the partial with respect to y of y times z. Okay. So on the right hand side is 0. Okay. So now let's continue. So to equivalently write this equation, so we mentioned okay, the beginning term is a 0, so it's going to be gone. So 3y squared plus 3z squared del z del y. And now here we're going to do the product rule. Okay, so y is a function in terms of y, of course. Z is a function in terms of y also. So it's here, it's going to be the derivative of the first times the second plus the first times the derivative of the second. Okay, the derivative of the first is 1 times the second plus the first times the derivative of the second. Here is the partial derivative of the second. Okay. So that's good. So product rule. So yeah, let me just write product. All right. If this is good, then we are almost there. Here we have the equation and it looks complicated, but recall what do we want? We want this. We want del z del y. So we here want to rearrange the equation so that everything about del z del y is on the left hand side, everything without del z del y is on the right hand side. So here I'm gonna quickly do the rearrangement. So we see 3z squared in front of del z del y, right? And then we also see that we need to distribute the second we need to distribute that the product as 6x times y. That's in front of del z del y. Okay, so we keep this on the left hand side, and on the right hand side we just move everything without del z del y on the right hand side. So this is negative 3y squared minus 6xy. Excuse me, 6xz. Okay. So solve for del z del y. We have the final result. Okay, so the division about the the bracket here. So as a denominator. Okay, so here, if you want to simplify a little bit, you can divide both top and bottom by 3, but that's not really required. The top view is the derivation of partial derivatives. Example. So we have two partial derivatives. Basically, we want to illustrate that in a two-dimensional figure for a binary function f of x y. Here we're gonna let the function to be 4 minus x squared minus 2y squared. So this is actually a nice quadratic function. So here, if you think about it, when you're sketching the graph by using the traces, then if you fix the x value, you will have a parabola opening downwards in terms of y. If you fix y as a constant, then you will have a parabola opening downwards with respect to x, right? So that's actually an elliptic paraboloid. So if you fix z, you'll get an ellipse, right? So graph of f is the following. So basically, if we just fix x to be 0, like we mentioned, this is gonna be a parabola opening downwards. And then when you fix the v value, it's gonna be an ellipse. Right? So that's the bottom is actually the xy plane with the xy trace. XY, and the vertical is going to be the z-axis. So this whole thing is the graph of the function that we defined above, right? And then the beginning curve is actually the yz trace, where we fix x to be 0, and then we have z equals to 4 minus x squared, right? But wait, when x is 0, it's minus 2y squared. That's the top curve right here. So this is the surface. And of course, we mentioned that the bottom ellipse is actually where you fix z to be 0. And so this is on the xy plane. So z is 0, you have 0 equals to 4 minus x squared minus 2y squared. Okay. And if you simplify further by moving xy on the left hand side and then dividing both sides by 4, you will get the standard equation for the ellipse. Okay. And now we focus on the first octant. And here, basically, when we talk about the first octant, this is just the part where x and y are non-negative, and z also is non-negative. So basically, we'll be looking at this piece. So this is a part of surface that's having x, y, z components, coordinates to be non-negative, right? And here we are able to even calculate these intersections. So that's actually where you have y and z to be 0. That's actually x equal to 2. When we have x and z to be 0 on the y-axis, you actually have a square root 2 right here. And here this is z equals 4. Right, when x and y are zeros, you have a z equal to 4. Okay. And now let's look at the point, input point 1, 1. So when x and y are equal to 1, so I'm gonna put it right here. Okay. So this is 1, 1, 0. Okay. So that's telling us if we fix the x, y to be ones, and then, well, in the three-dimensional picture, the location of the input point, right? And then eventually you want to look at the behavior of the function on the surface that's having x, y coordinates we want. So here we have, yeah, the purple. I'm gonna use the purple here. So this is a specification with x, y, z to be non-negative. Okay, so that's the first octant. Consider f sub x at 1, 1. So this is the partial derivative with respect to x at the input point 1, 1, right? So if we do the calculation, it's actually straightforward. So the function is right here. It's z equals to 4 minus x squared minus 2y squared, right? So f sub x, the partial with respect to x is actually, so we're doing the partial with respect to x. So the first, the constant gives you nothing. Negative 2y squared gives you nothing because y now is fixed. X is going to give you negative 2x. Okay. So we can plug in the pair 1, 1, and then we'll be able to calculate this partial directly. So plugging x equals 1 and y equals 1 right here. That's a negative 2. So we see that this is the instantaneous rate of change with a value negative 2. And also we recall this actually is exactly the value, the instantaneous rate of change that we get when we fix y first, right? Recall that if we fix y first, we'll get a function g, okay? So this is exactly the derivative of g at the input level 1, where our g function, right here, g function is exactly the restriction of our function where my y value is evaluated at 1. So that's actually on the top we have what? We have 4 minus x squared minus, now we're plugging y equal to 1, that's actually negative 2 here. So this is 2 minus x squared. Okay, so now thinking about this step. So this step is actually doing what? This is actually saying, okay, I'm fixing y equal to 1. Let's say I'm intersecting the surface that I have at the top with the plane y equal to 1, right? And then g prime is actually what? It's actually the slope of the tangent for that curve. Okay? So that's something we're gonna illustrate right beneath. So note that intersection of z equals to 4 minus x squared minus 2y squared, this function, and the plane y equals 1 is exactly the g function. Okay. So the function that we have, and we intersect with the plane, and this is exactly that substitution step, right? And here, if you actually substitute the y value here, you will get that g function. But still, you have to specify that you are on the plane y equals to 1. Okay, and now we can draw the figure. So, let me think. So the surface on the first octant, let's just do the illustration like this. Let me make it a little bit curvy. So x, y intercepts, z intercept. X, y, origin. And now here, we have the points 1, 1, 0 right here. This is the point. And now y equals 1, right? So this is square root 2. Let me also just put the intercepts. So square root 2, and here we have 2 for x. Okay. Now let's illustrate that y equal to 1 plane. Okay. So here it has to be parallel to the x-axis, and here it has to be parallel to the z-axis. Right? So this dashed lines, that's indicating that we are on the plane where we have y value equal to 1. And then it will intersect the surface on the top, right? So you see, this is actually a quadratic function. It's actually a parabola opening downwards. It follows along the shape of our surface on the top, right? And then if we illustrate this solid point vertically up, this is the functional value that my z value is essentially 4 minus 1 minus 2, right? That's actually what 1, 1, 1 right here. 1, 1, 1, right? So the purple curve right here, this is exactly my quadratic function fixed on the plane y equal to 1. Okay. So now we do have every piece. We have the function g, that's actually the purple curve opening downwards as a parabola. And also we mentioned that g prime of 1 is actually what? It's actually that partial derivative, right? -2. And then it's the sum of the tangent, right? So if we get a closer look, so we have the red dashed axes. Okay. And then we have a purple parabola opening downwards, right? And then we have the solid black point vertically up. That's our functional value 1, 1, 1 right there, right? And finally, so this purple curve is actually the g function, okay? And then g prime is what? G prime is the tangent line. Okay, we want to maybe make it black. So it's gonna be a tangent going through the point. Okay, tangent line. Okay. And here you can see that the slope should be that's -2. Okay. So since my partial with respect to x is g prime of 1, we know that f of x at 1, 1 is the instantaneous rate of change del z del x with y fixed at the level 1. Okay. Or equivalently, the slope of the tangent line of the parabola in purple, of course. And here I'm fixing the input level to be x equals 1. And that parabola is exactly z equals to 2 minus x squared. So it's just the purple equation that the purple system of equation that we have already at the top. Okay. And now this actually is on the plane y equal to 1. So let me get that figure right here and put in some more details. Okay. So the right-hand side figure is actually an illustration, but of course we can get the more details on this figure by filling out the axes. Okay. So you know this horizontal one is actually the x-axis. This is the z-axis. Right? Actually, we are on the plane y equal to 1, right? So this purple curve is actually z equals to 2 minus x squared. And then this point is where we have x equals 1 right here. And also the output is z equals 1, right? The height. And here we just want to indicate that, okay, we're looking at the slope, right? We're looking at the slope of the tangent, right? The slope of tangent is del z del x, okay? So the instantaneous rate of change of the z value in terms of x, right? And this is exactly the partial evaluated at my input level x equals 1. So that's our -2 here. But in the figure, not only we can know the slope, but we can also write down the equation of this black line now, right? We have the slope. We at this location we gave the coordinates, right? We know the black point here has coordinates x equals 1 and z equals 1, so we can write down the equation of the tangent. So it's the point and slope form. So we go through z equals 1, x equals 1. Excuse me, x minus 1 here. So that's the point, and then you can put the slope in front of the x portion, right? So this is the tangent line. Okay. So this tells you on the plane y equals 1 right here, we have the equation of the tangent line. We obtain a tangent line. So we do know the equation. So here you see that -2, the partial derivative is now the slope of this line that we established. Okay, z equals, so basically we're just writing down that line equation again. Okay, so this portion and this portion, that's the x and z values at the points. But the -2 is the slope, okay, which is the instantaneous rate of change. But we still specify the location where we are on the plane y equals 1. Okay. So any questions regarding the process right here? So basically, the most important step is actually the fundamental step of fixing the plane, right? So we are saying, okay, my y value is treated as a constant, where I'm doing the partial with respect to x. And here it happens that the plane is y equals 1. Okay. That's good. Right. So now, an important remark. So now we do see that exactly what that partial derivative is representing. Okay. So this actually this process actually works for any function and any input pair. So for function z equals to f of x, y, the partial derivative with respect to x at the point x0, y0 defines a tangent line of the graph z equals to f of x, y at the point x0, y0, z0. Here, my z0 is the functional value of f at the point. So we can write down the equation of the of this tangent line directly. Okay, so we specify that the y value must be y0, since we're doing the partial with respect to x, right? But then we can write down the equation of the tangent line here. So basically, z minus z0 is the z coordinate, right? This equals to the slope times x minus the x coordinate. And then what's the slope? The slope here is exactly that partial derivative, okay? Instantaneous rate of change. Right? So that's the equation of the tangent line. And move down a little bit. So this is exactly the process we have done in the figure. And similarly, if we are looking at the partial derivative with respect to y, it's going to be a similar process. And that will also give you a tangent line. At the same point. But then we just need to realize that when we are doing the partial with respect to y, then we are fixing x. Okay. So here, if you want to write down the equation, is going to be x equals to x0. Okay. And now then y and z are changing. So it's going to be z minus z0. That's the point so for y minus y0 right here. And then the slope is going to be this partial derivative. Right. So now, if you recall, this line is actually the line that the tangent line that we established in the figure above, right? And also, this is just another tangent line that we can also illustrate in the figure. So let me quickly copy the figure from above and illustrate both lines. Okay, so basically right here, right? So basically the figure right here, we're gonna reuse it. So the purple curve is the quadratic, right? So we are actually drawing the tangent line. Let me think. Let me make it in red. So basically, for the first tangent line, it's actually tangent to the purple, following the same direction as the curve. Okay. So this is and also it's within the plane y equal to 1, right? But then if you look at the other partial derivative, that's actually saying what? That's actually saying, okay, I'm fixing x to be 1, so that's another plane. So it's parallel to the y. It's parallel to the y-axis. And z-axis here. And then the curve is also a quadratic downwards. Okay. And the other tangent line is also following along the direction of my purple curve right here. Okay. And also it's within the plane x equals 1, right? Okay, so that's 1. So these are the two tangent lines. So once again, this is the surface z equals to 4 minus x squared minus 2y squared. Yeah, right. Okay, so now we have two tangent lines. Okay, so these are the tangent lines we just illustrated to have the slopes to be the partial derivatives. Okay, and now so let me think. So we have each tangent line in red to be tangent lines to these restricted quadratic curves, right? So here you can imagine that these two lines will form you a plane. So there will be a plane that's containing these two straight lines, right? So this is something you have seen already from the first chapter of our course. So basically, what we see here is that we have a line in red, we have another line in red, right? So you should be able to write down the equation of the plane that's actually containing these two lines. Okay. So this is eventually this plane is called the tangent plane. And here in homework 6, you are asked to write down the equation of this plane containing the two lines. Okay. And so I think you should be able to handle this kind of question. So homework 6. It will be published later today. Okay. So this is the geometric perspective of these partial derivatives. Now we have more general situations. So functions of several variables. So if we have more variables, actually the partials, we just have more partials, but the idea is the same thing. So let's say we have a function in terms of x, y, and z, and let's do the partial with respect to x, y, Okay. So if we have a three variable function x f of x, y, z, and we do the partial of the x, so that's basically saying, okay, I'm treating y and z as constants. And then this becomes a univariate function in terms of x, right? And then I'm able to do the derivative, which is the partial derivative in terms of x. So by definition, it's going to be the limit where my change in input is only going to be at the x component. So this is going to be f of x plus h y z minus f of x y z. So the change in the output is only produced from the tiny little change in the x coordinate, right? And in general, for a function that has more variables, let's say a function is u, which is f of x1, x2, all the way up to xn. So it say there are n variables, and then n could be any number. Then in this situation, we still can define the partial derivative. Okay, so it's the same idea. For any partial derivative, we just fix all the other variables as constants, and that will give me a univariate function. Okay, so we have for any index I from 1 all the way up to n, I can define the partial of the output u with respect to xi. So in terms of the notation, we can also write del f del xi. We can also write f sub xi, or even we simplify it to be f sub I, because I'm just doing the partial with respect to the ith variable, so I can even just omit that x. And we can also write it as cap d sub I of f. This is just saying I'm doing the partial derivative with respect to the ith variable. And although we have different notations, but the definition is exact extension of the above. So this is just saying, okay, I'm just taking the limit where my increment of the input is approaching 0, and I'm just doing the rate of change. Okay, so it's the change in output over the change in input. And then the change in output is only taking place in the ith component. Okay, so this is f of x1 all the way up to I minus 1. So the first I minus 1 components are not changed at all. The ith component, this is xi, I'm doing the partial, right? So this is xi, I increase by h units. Xi plus 1 is not changed at all. And all the way up to xn. So only this component is changed. Okay, every other component, they are just fixed as constants. Okay, and the same for the latter entries. Okay, so these are fixed constants. So this is the latter output minus the prior. So the prior is exactly f1, f of x1 all the way up to xn. Okay, so here this no argument is changed. Okay, so you can see that only the ith component is increased by h units. So that's the direct extension from here, right? So here we're doing the first partial derivative. So that's just changing the first component. So you just need to keep in mind that whenever you're doing the partial, every other variable is fixed as constant. Okay. So example. So let's look at some function that's having three variables. So let's say e to the xy times ln of z. Okay. So now let's try doing the three partial derivatives. We have f sub x, f sub y, f sub z. Right? So f sub x. So basically, when you do f sub x, you see this is a constant, which is multiplied to the exponential function right here. Y is another constant in front of x, right? So when you're doing the partial, you actually have a composition. So we have e to the y times x, right? So y times x is actually a linear expression as the inner function at the exponent. Okay, the outer function here is the exponential e to the something. So when we are doing this kind of partial, we need to know that this is a chain rule. So e to the something is the outer function, right? The derivative of the outer is still the e to the something. Plug in the inner x times y, and then so the derivative of the inner. So this is a linear function, right? So the derivative of the inner is exactly y. I'm gonna put it in the front. And that's the derivative of our exponential part in terms of x, right? And then I multiply ln of z, which is a constant. Multiply it. Okay. So it's good. Okay, so now let's look at x of y. It's gonna be really similar. So now when we're doing the partial respect to y, so I'm gonna treat x as constant, ln of z as a constant. So this is a constant times e to the some constant times y, right? So it's the same idea. So I'm gonna keep ln, so it's gonna be ln z, that's a constant multiplied in the front. And then e to the xy, right? X is a constant, y is changing, so it's a composition. The inner is a linear function, x times y, the outer is the exponential. So I'm doing the derivative of the the derivative outer, evaluate the inner, and then I do the derivative of the inner, which is so here this is x because I'm doing the derivative of the straight line. Okay. And finally we have z, x of z. So now we see when we do the partial derivative of z, this whole thing is a constant. So it's just a constant times natural log of z. And we just need to realize the derivative of natural log is just 1 over z. Okay. So it's e to the xy, which is constant, whole thing of this. Any questions so far? So you can see we are indeed getting into the calculus part of the course. Okay, so this is it will get more and more involved starting from this partial derivative concept. Good. Right. So now the next topic is the following. So now we know how to do the partials, right? And then you recall that there are like second order derivatives and third order derivatives, right? In univariate case. So actually that will also occur in terms of the partial derivatives. So high order partial derivatives. Higher or high order derivatives. So let's just look at the bivariable function again. So we have two variables, x and y. So firstly, we introduce the notation. So when you do the partial with respect to x, you can, so this is the bivariate function, right? So f of xy is a bivariate function, so f of x is also a bivariate function. So you have the option to do the partial with respect to x again. So this is the first notation that we can see for the order 2 partial derivatives, right? But then we can abbreviate this notation by getting rid of the brackets. So it's f sub xx. So this is good enough to indicate that I'm gonna do the partial with respect to x first and then x again. Okay, f sub xx. And also I can just write f sub 1 to indicate that I'm doing the partial with respect to the first variable and then with respect to the first variable again. Okay. And what about the Leibniz notation? So if you think about the Leibniz notation, f sub x is what? F sub x is del f del x, right? And then I'm gonna do the partial with respect to x again. That's doing the partial derivative on the left-hand side as like an operator. Okay. So this is what? This is the del x of del x. Kind of complicated, right? For the Leibniz notation. But if you look at this, you see this portion, this is like operator doing the partial. This is the same operator, right? So they have a way to abbreviate by saying I'm just doing del squared f of del x squared. You see, here I'm just putting this to be squared to indicate that I'm doing this twice. And here I can also change the variable by putting a z here. So if I do del squared z, del x squared, that's the same meaning. Just saying I'm doing the partial with respect to x for twice. And similarly, if we have the partial derivative of y, and then we do the partial with respect to y again, so this is going to be f sub y. This is saying I'm doing the partial derivative for the second variable, and then I repeat. If you want to do the Leibniz notation, it's going to be del y of the partial of the function with respect to y. And then you can combine the operators by doing del squared, del y squared of f. And that's the same as doing the thing in terms of z. And then there will be more options, right? So here we did the partial with respect to x, and then x again, or we did partial with respect to y, and then y. So you can do like a mixture, right? So f sub x and then sub y. That means what? That means I'm going to do the partial with respect to x first, then y. Or if you want to do it in terms of the index, it's going to be the first variable, then the second. Okay, so the order matters very much. And then if you want to do the Leibniz notation, so basically this is del f del x that we do first, and then we do del y. Okay, so you can see by observing the difference of order, right? So the indices on the left-hand side, this is going from the inner to the outer. But here, this is from the right to the left, right? So I look at the operator on the right first and then left. So although they have a different order, but I just want to emphasize that the operator that you look at first is the one that's closer to your function. Okay. So that's true for both notations. So the operator that you do first is the one that's closer to your function notation f. So if you want to combine, you can see here I have del's on the top, that's going to be squared. But then I'm going to keep del y, del x the same order as you have seen from the left. So you cannot really combine that as a square, but so that's the way that you do the Leibniz notation. And of course, changing to a z is also fine. And you see here the order matters, right? So you cannot really interchange the order directly. So the closer one is x. So that tells you I'm going to do the partial with x first. The next one is y, right? So that's the second operation I'm doing. And similarly, f sub y, then f sub x. That's just let's play with it. So this is f sub yx. This is saying I'm doing the partial with respect to the second variable, then the first. And then I'm doing del f del y, and then I'm going to do the partial with respect to x. Okay. So here on the top, I can combine the del's, but on the bottom, I can only just preserve the order by doing del x del y. And finally, I can replace my app to be z. And you can see the difference. So these are all the order 2 partial derivatives, and of course you can go higher. So let's say we have f sub xy and then I sub y. So this is just saying, okay, I have this partial derivative right here, but then I'm gonna do the partial derivative y again. Okay, so in terms of notation, now we follow the pattern, right? So this is just f sub x y y. Then by the order of the letters or indices, that the closer to a function, this tells you, okay, I'm gonna do the first variable, then I'm gonna do the partial to the second variable, then the second variable. Okay, so that's 3 times. And then to follow along the notation from above, so we have del y del x first, right? From the line above the previous. So this is the inner, right? And I'm gonna do the partial to y again. And you can see this part actually is the same as this part. So this, if I want to combine everything, I can combine the squares for this del y. Okay, so this is actually del cubed of del y squared del x. Okay, so here we have del y and del y. They're together. They are neighbors. So I can combine those. And well, if you want to switch it to z, that's also an option. Okay. Right. So now we do get the pattern of the notation. So let's look at an example. So let's look at the function that's not so complicated as a polynomial. So x cubed plus x squared y cubed minus 2y squared. Okay. So now let's play with the higher order partial derivatives. So of course, we should be very familiar with the partials by now. So f sub x. So here we treat y as constants. So we should have 3x squared. There's no constant here. Plus, so x squared gives you 2x. And then we keep y to the 3 as a constant. And finally, the last term doesn't give you anything because it's not changing when x changes. Okay? Now f sub y is going to be similar. So x to the 3 does not change, it will give you nothing. Y to the 3 gives you 3y squared. And here I'm keeping x squared as a constant multiplying the front, minus 4y. Okay. And now let's look at so far any questions. So that should be good, right? Partials. And then what happens if I do f sub x, f sub xx? So this is saying, starting from here, I'm gonna do the partial with respect to x again. Okay, so it shouldn't be any different as long as we know how to do the operations. Okay, so now we do the partial with respect to x. So it's gonna be 6x plus now 2x gives you just a 2, right? And then we can, we just write out all the two partials. So we have f sub xx, right? We have also x sub xy. Actually, it's from the same row, but we are just doing the partial to y. So it's the same. It's the same f sub x. Now we're just doing the partial to y. So 3x squared gives you nothing. 2x is a constant in the multiplier. Y to the 3 gives you 3y squared, right? So it's going to be 6xy squared. Okay. So that's good. Any questions? But if it's good, then let's do f sub yx. So that's actually looking at this row. Okay, so this is saying I'm doing a y first and then x, right? So here, if I do the partial with respect to x, what do we see? So 3x squared, that gives you the partial, which is 6x. Y squared is a constant multiplying the front. And finally, for the 4y, it's not changing when x changes. Okay, so we can see, okay, this result is the same as the previous line. Right? So it's kind of tempting to conclude that f sub xy and f sub yx may be always the same. Okay, and of course we have f sub yy as the last order 2 partial derivative. So that's still from the same rule. We are doing the partial derivative y again, so it's going to be 6x squared y minus 4. Let me see. So one more line. So observe that f sub xy equals to f sub yx above. Okay. So this is true for at least for our instance here. So here we see, okay, f sub xy equals to f sub yx in this situation. This is actually a really important theorem in multivariate calculus that's called Clemon theorem. So indeed, so these are partial derivatives, f sub xy and f sub yx, they are possibly identical, but there's a condition. If f of xy is defined at point AB, and the partial derivative, the second order partial derivatives, f sub y, xy, and f sub yx are equal. Well, excuse me, they are continuous. Are both defined and continuous. At the point AB, then the evaluation of these multivariate functions at point AB are gonna be the same. So you can see that f sub xy is you do the partial with x further than y, it's gonna be a multivariate function. Okay. And this will be another multivariate function when they are both well defined. And here we do require that these multivariate functions, these two multivariate functions, they have to be continuous at the point AB in order for this to hold. Okay. And it basically tells you in certain situations when your partials, when your second order partials are not continuous, then this is highly likely not to hold. Example. So let's look at a three-variable function f of x, y, z as defined as sine of 3x plus yz. We want to find f sub x, x, y, z. Okay. So now we are doing a order 4 partial derivative. Okay, so if you're looking at the notation, this tells you the closer the subscript is to the function, that's going to be the earlier operation, right? So you have x, x, y, z. So as this order, you have to do the partial with respect to x, and then x again, and then y, and then z. All right. So we just do it systematically. So x sub x. So it definitely involves chain rule again, okay? Because you have the inner function, which is a linear function in terms of x, which when you fix y and z as constants, or if you treat y only, or if you treat z only, right? Treating all the other variables as constants. So here, if you do the partial derivative of x, you see, okay, it's a linear function on the inside, it's a sine function on the outside. So you have to utilize the univariate chain rule. So the sine function, the derivative of the outer gives you a cosine. And then you plug in the inner function in terms of x. It's just that the inner function expression there. And then you multiply by the derivative of the inner. Okay, now 3x gives you a 3. YZ is not changing, so it gives you nothing. So we have a 3 in the front. So it's good. So this x becomes really standard. Okay? And then we do f sub x again. So basically, based on f sub x, we do the partial with respect to x again. So in this situation, you see, okay, it's 3 times cosine as the outer function, the same inner function as the linear one, and we expect to get the same kind of format. So the derivative of the outer is so cosine gives you a negative sign. And we do expect that the constant on the outside is it starts from 1, we got a 3, right? And then if we do it again, we should get another 3, right? So we will just leave the blanks for the constants. And then it used to be 3. And then we derivative of the outer, we evaluate the inner, we just plug in the inner, and then we multiply by the derivative of the inner. So that's a 3, right? So we originally we have a 3, and here we multiply by 3, that's going to be a 9. So that's good. Okay, I see some of you are nodding, so that's good. So let's do y. Okay, f sub x to y. So now when we look at y, well, the inner function is still this, but it's a little bit different in the sense that in front of x is a 3, but in front of y we have a z. Okay, so now z is that constant multiplier in the front. The outer is still some pre-function, so we need to be careful. So so let's keep that negative 9 in the front for the moment. So the derivative of the outer is going to be cosine, and then we evaluate the inner, and then the derivative of the inner. So now we are doing a z in the front. Okay, and then negative 9 is just copied up front as a constant multiplier. That's good. Okay, so now finally you will see that we need to do the partial with respect to z. That's the last step. But now it gets a little bit complicated in the sense that we have a z in the front, and we have a function of z in the trig part. Okay, so now we have a product. So it tells you now it's a product of the univariate functions in terms of z. So we need to be careful. It's going to be a product rule. So f sub x, y, z. Now so you have the product of two functions in terms of z. So you know the product rule tells you need to differentiate the first function, then multiply by the second, and then plus the derivative of the second function multiplying by the first. Okay, so we write that down. So the derivative of the first is easy. So negative 9z gives you a negative 9, and then we just copy the second function. Now plus, now for the other part is going to be the first function times the derivative of the second. So let's just do del z of cosine 3x plus 1z. Okay. So I just wrote the d, but then I realized, okay, it's a multivariate function, so it has to be a del instead of the d. And now we're almost done. Okay, once we do that partial derivative with respect to cosine again, it's going to be done. Right. So let's copy the thing from the top, and then realize that we are doing the partial of this cosine. So cosine is the outer function. That 3x plus yz, the linear function, is the inner. So the derivative of the outer is so yeah. Let's write one more step. So just copy the thing in the front. So cosine gives you a negative sign. Evaluate the inner. We plug in 3x plus yz, and then the derivative of the inner. Okay, so multiply by the derivative of the inner. Now it's the partial derivative in terms of z. So y is in front of z, so we have a y there. Okay. And here you can see we can simplify by just the two negatives make a plus, right? And then we have just 9yz in the front. So -9 cosine 3x plus yz plus it's 9yz sine of the same expression. So it's good.